So it's my pleasure to introduce Gregory. Gregory's been here way too long, so I'm glad
This means I have to pass.
Finally finishing. He's been a wonderful student. He's worked on a huge range of things. He started working on VHDL as an undergrad, right? And I always imagined he would come in doing hardware-related stuff, and he's about as far from that now as you can get. But he was a big part of the Why Not project, which Adam was involved with early on, and now he's been actively engaged with Adam's group on the Bedrock effort, as well as a bunch of other things, which you'll hear about today. So take it away, Gregory.
Thank you, Greg. Thanks everybody for coming. So this talk is about extensible proof engineering in intentional type theory. And I'll get to what that means. For the most part, as Greg mentioned, I do a lot of proving things, and so I'm interested in the engineering aspect of those proofs, and I do it inside of this theory called intentional type theory. I'll tell you what that means. As soon as I can work my clicker. All right, so what I'm interested in is mechanized reasoning. Things like domains like math and software both are, it's useful to do in both of these ways. In mathematics, we've got big proofs. I don't know what this actually means, but it came up in Google image search when I did search for math. Actually, higher category theory is not something that Google image search is good at finding you. Anyway, so all of these lines kind of mean things in a category sense. And if any of them are flipped or something doesn't match, then you could end up with a result that is not true, but you think is true. And checking these things can be quite difficult. Now, not many people here are higher category theory people, myself included. So I'm going to focus more on software engineering. And so here we've got a few things. And primarily we're interested in constructing boxes that look something like this. Compilers fit into these boxes. They take in C files. They spit out object files. And kind of on the side, often you have optimizations that might apply to certain C files and not to others. So we'd like to talk about adding optimizations after the fact and retaining kind of a nice artifact that we can run. Other things we have are things like static analyzers, which take in C files. Think about properties of those C files, like no index out of bounds exceptions or things like that. And it kind of gives us a check mark that says, yes, that property holds, or an X saying, no, that doesn't. Here, we also have interesting heuristics that we might need to do to figure out what sorts of invariants we need, what sorts of information we need to track. And the thing that I'm going to be most interested in here is program verification. And here we've got a whole array of things that we have to think about. So things like adding theorems, domain-specific theorems, heuristics for doing search, and then things like invariants that occur throughout your program. So the question that I'm going to ask is, how can we build these things? How can we build them efficiently, and how can we build them so we know that they're correct? And I'm going to instead focus on program verification. So this is my thesis. For the time being, let's just take a look at the last 4 words, or the last 5 words. First thing, we want these boxes to be trustworthy. I'm going to signalize that with this little certificate of goodness. We want them to be scalable, handle large files, large inputs. We want them to be composable, so we'd like to build the full box out of small boxes, kind of piece it together after the fact. And what I mean by customizable is I'd like to be able to take a box that's already kind of constructed, like tack on another box. This is a composability aspect, but we want this box to be kind of easy to construct so that it's easy enough to construct to apply it to a very problem-specific thing. Like, for example, reasoning about something like a linked list might only require reasoning about this certain predicate. The way I'm going to do this is I'm going to use some techniques that exist already. Computational reflection and intentional type theory are 2 of the main things. I'm going to talk about what they mean. And the combination of these 2 things, so intentional type theory, is going to get us the trustworthiness that we're looking for. And computational reflection is going to get the scalability that we're looking for. And I'm going to talk about the composability and customizability in my contributions after this. So there's a whole range of logics that we could use to gain our trustworthiness from, things like ACL2, Isabelle, Coq, New Perl, great examples. I'm looking at the foundational ones, the ones on the right here. So theories like Isabelle, Coq, and New Perl, the main thing about these is they have a small kernel. And the key insight of a small kernel is that we can separate the checking aspect that we actually have to trust from the complicated heuristics that we use to construct proofs. So, key thing here. So every time you see this guy, this is a note to me saying you should explain this because someone in the room might not know what this is. This is a proof tree. The bottom here is the conclusion, the thing we're trying to prove. We're trying to prove A and B and C implies C and B and A. And the proof tree is kind of going to spell out every single step that we need to do. So first we apply the commutativity of and then the commutativity of and then the associativity of and. And I'll always elide the final step where we have reflexivity. So like I said before, the key thing here is that in a foundational proof, we have to spell out every one of these steps. And now we could do it manually. That would be kind of annoying. Even this simple thing might be kind of complicated to see, should I apply associativity first? Should I apply commutativity first? Things like that. So we've built a lot of techniques. Things like automation. LTAC is a tactic language for Coq that I'll talk about only briefly in a minute. We can think of this as saying, try to do all of these things. See if we've already solved the goal. See if it's the same on the left and the right. Or try to apply commutativity or try to apply associativity. Just kind of blindly do this until you solve the goal. That'll get us a proof. The thing is this tactic is going to construct this proof tree. And this proof tree will afterwards be checked by the kernel. So we're going to build this using this piece of automation. We're going to pass this. We're going to pass this proof tree off to the kernel. The kernel is going to say, "Yes, I accept this as a proof. Your fact is true." The key thing to note is the kernel is forced to look at every step in this derivation, and it's not allowed to use any really sophisticated algorithms. Like if it knows that and is associative or something like that, it might be able to derive this fact automatically without looking at the proof tree. We're not going to let it do that because we're not going to have any of these symbols kind of built into the theory. All right, so we're in this foundational setting. Another line we can draw here is the intensional versus extensional setting. And here this divides off new Perl as an extensional type theory. And that is interesting because it is an undecidable language. So if I have a proof and let's say Yuri and Drago both implement my proof checker, it's possible that I give my proof to Yuri, and Yuri says, I accept this as a proof, and I give it to Drago, and Drago says, I don't accept this as a proof. And that's because maybe he didn't implement the same heuristics that Yuri did. So what does this look like? Kind of the source of undecidability in these logics is this conversion rule. Thinking about what this says, it says, you can prove P on the bottom if you can prove Q and P is in some sense equal to Q. This is a meta-logic equality. And in the extensional world, this equality is just provable equality. So anything if any two things are provable in the logic as being equal, then they're kind of considered equal and you can use this rule. In intensional type theory, there's a little more restriction. We're going to require only that P evaluates to Q. And this isn't quite true. There's a little bit more complexity here, but for the purposes of this talk, simply talking about this as straightforward evaluation will be enough. All right? How many people have I lost? No one in my thing. The key thing here is we're going to execute this turn. All right. So, another line that we can draw here is computational. This is the conversion rule we just talked about. So all of these logics up here are computational. And the key insight of computational reflection is we're going to use this notion of computation in order to compress the proof objects. And if we can take a look at the rule, this star here is allowing us to do kind of an arbitrary number of steps. We can run this term as long as we want because we know it's going to terminate. And that is going to allow us to take a proof that was maybe many of these horizontal lines and compress it into one horizontal line and try to take all of those lines and make it into this evaluation relation. Let's take a look at what that means. So here's the proof we've been looking at, this conjunction proof. The first thing we're going to do is we're going to build a syntactic world, a syntactic representation of this proposition. So here I'm using these blue conjunctions with the underlines to say this is a syntactic object as opposed to, call it the semantic object that lives over here. That's what you think of as conjunction. All right, so we're going to use this conversion rule here. The key thing is this goal is the same thing as this goal by the conversion because we've applied these Oxford brackets. And what that means is it says, take the syntax and figure out what it actually means semantically. And so basically we can think of this operation as taking these blue conjunction symbols and turning them into black conjunction symbols. Then we take this soundness proof here. It's going to, we'll write a function, rtauto. It's going to be this function that's going to decide or semi-decide properties like this. So it'll get in this piece of syntax and it'll compute an answer. And if that answer happens to be true, like it is in this case, then we can use the soundness theorem of it here that says, if rtauto takes in some goal, any syntactic object, and returns true on it, then that object is actually provable. So we're going to use this theorem here to construct this line. We will then use the conversion rule on this left-hand side to compute it down to a normal form. If we get true out, like we got here, we'll have true equals true, and that's trivial to prove. So what we've done is we've traded this proof for this, unfortunately, equal-sized proof. But if you add more conjunctions here and more conjunctions here, then this proof explodes while this proof maintains essentially the exact same size. Because of all of the complexity that's going into this reasoning here is encapsulated in this soundness theorem and is noted or is kind of witnessed inside the computation step that's going from here to here. Right? Any questions about this up till now? Go ahead.
Seeing that rtauto is equal to true, does this get slower as your conjunction gets bigger?
So in theory it does. It turns out that in practice, execution of programs is really fast. So we'll essentially consider this to be very cheap. This computation is very cheap. All right. So I told you how we use computational reflection to get scalability. We're going to be able to scale to larger formulas. We do this in intensional type theory. That gives us trustworthiness. So now I have to tell you how what I did, all of my work is in the open part of this open computational reflection, and how that allows us to build bigger boxes from smaller boxes, and how it allows us to build small boxes cheaply. All right? So let's take a look at what this problem might look like. Let's say we have one box here, rtauto, that we talked about in the previous slide, and we have another box for reasoning about arithmetic. And what we'd like to do is we'd like to construct the box, or now rectangular prism, that handles both of them at the same time. And so here we've got a problem like true and something, but if that something was something simple like a plus b equals b plus a, then we'd like something like this arithmetic and logic solver to be able to prove this entire derivation kind of in one shot. So, coming along, we have a syntax here. That was the true and that we saw in the previous slide. Our arithmetic language might have equality and addition inside of it. And we want to find some way to glue these two languages together. Now, Benjamin, Delaware, in the audience, has a wonderful way to solve this problem, and other previous work has other ways to solve this problem. But we're going to choose something a little bit simpler. And the idea here is inside these languages, there's really a common piece. So we can think of the logic language as having symbols like true and, but also using kind of an application rule here. This is, instead of thinking of this as an atomic thing, we can think of it as and applied to P1 and that thing applied to P2. So we've factored out the kind of the passing arguments and handled the recursion within this language called the lambda calculus, which looks something like this. So if we want to represent the formula at the top inside this enriched language, it looks something like this. So we have the symbol x sub and. That's the and coming from the logic language. And it's applied to x sub true, which is also coming from the logic language. And that second argument, this P2 here, is actually coming mostly from the arithmetic language. It's this equality applied to the left-hand side, which is a plus of A and B, and the right-hand side, which is a plus of B and A. Okay? So we've factored out kind of the difficult recursion into this language here. And this is one of the key insights of the work I'm going to talk about. The key thing to note here is that in order to reason about this language, we have to define the denotations, and they get defined independently. So this is allowing us to say the denotation of this lambda language given this extension is just the denotation of the lambda language and kind of the denotation of its extension in an independent way. And so the soundness theorems that we are going to phrase, that R Tato sound that we saw in the previous slide, has to reason about this denotation function, and that's where all the complexity comes in. Kind of unsurprisingly, proofs are hard. Here's what it looks like. So we've got our lambda language, and we've got our conjunction, our logic language, and our plus and equal arithmetic language. And this cloud down here represents the semantic universe. Yay. Each one of these has its own representation. So if we take the denotation of these pluses and equals, it gives us some space over here over there. And if we take the denotation of and true, we get some space over here. And the whole thing that we have to worry about is when these things overlap, we have to make sure that they're consistent. Okay? And what this consistency is giving us is something simple. It says, if R Tato ever needs to call the arithmetic procedure, it might ask the question, can you prove this formula G? And the arithmetic procedure will say, yes, I can prove that formula G, but I proved it under my thinking, what I thought the meaning of G was. And you asked the question under what you thought G was. So it's important that what I think I'm asking you and what you're answering are the same thing. This is what's giving us the ability to import results from arith into our R Tato. All right? So the next two slides, or the next few slides, will tell you the way that I achieve this. And for those of you in the audience who are not intentional type theory people, this is where you can go to sleep. Come back. I'll tell you when you can come back. Enjoy your coffee. We're going to start talking about explicit equality proofs. Okay? So here's my wall of cock code. Scare you all. So we've got language symbols up here. This is our representation of propositions, a representation of true and. We've got our reflective procedure, something like R Tato, which is a very simple recursion on this and saying, like, oh, if we're trying to prove true, then yeah, we can prove true. And if we're trying to prove the conjunction of two things, then we can just ask to see if we can prove each one of those. And then we have the soundness proof down here, which kind of looks reasonable, but we can't prove it enough right now because we don't know what the meaning of these symbols are. We need to know that true here is equal to true. The meaning of true is true, and the meaning of and is and. It's that standard denotational semantics mumbo-jumbo. The problem is in intensional type theory, we can't write this. And that is because this line right here corresponds to, or has a type error. This line, or this expression right here, has type the meaning of proposition. And that is equal to, provably equal here, to prop, but it's not definitionally equal to prop. Remember, in intensional type theory, we only get reduction, and this term here doesn't reduce. But if we were in an extensional type theory, we would say, this is an equality. We can import any provable equality into a definitional equality, and then we would get this to type check. So because I've restricted myself to intensional type theory, I cannot get this line to type check without a little bit of additional work. And that additional work comes in the form of casting. So this great red cast thing is saying, the thing on the right, or my argument, mentions tie prop, the denotation of tie prop. Kind of replace all occurrences of that with prop. And then this expression, the casted version, has that corresponding type. So when I cast this thing over here, from here to here, has type the denotation of type prop, but the casting of that has type prop. And so this becomes a well-typed formula. Throughout this proof, we'll see things like this. So this obligation is coming from the conjunction, the proof of the conjunction here. We say, we know something about we know that the cast of A is provable, and we know the cast of B is provable, We want to prove that the cast of A and B is provable. And that actually works out very nicely because of intensional type theory. What's a little bit more annoying is kind of the cast, when we cast by two different proofs, here PFP and PFQ, we can't use HA here to prove the goal here because we're using two different proofs. We can think about this as these proofs are representing the fact that when those two things overlap, they're actually the same. And here, we know they overlap, but we don't necessarily know that they're the same. Maybe we've done something kind of fancy under the hood. So this technique here, demonstrated by the slide, gives us very flexible composition because we can instantiate these things in any way that we want. But it's kind of very verbose, and it requires us to be very explicit about how we're maintaining our proofs. So a technique that I developed to solve this problem or ameliorate this problem is... Oh, sorry.
Where is the cast defined?
The cast is kind of a primitive in intensional type theory. This is just a match and equality proof.
Okay.
Yeah. And it's really a family because, you know, the type here isn't exactly proper. All right, so I'm now going to talk about a technique that I developed a while ago where we piggyback off of the definitional equality that we get for free in intensional type theory, and I'm going to use that to kind of get rid of these proofs and try to simplify things a little bit. So here's another wall of text, and people who are sleeping are still sleeping. That's good. What we're doing now is instead of quantifying over all possible representations of propositions true and, we're going to pick particular representations of them. Here, we're using numbers. So we're saying propositions are represented as kind of the number 1 used as a type, and the symbol true is represented as the number 0 represented as a term, and is represented as the number 1 represented as a term. We can write the same exact function here. I'm kind of cheating a little bit. The syntax is exactly the same as it was before. But now our denotation function, in addition to kind of when it wants to determine what x sub 0 means, it needs to know an environment of types and symbols in order to figure out what those things mean. And so here those are passed on to the denotation function. The slightly different denotation function works the same way. So let's zoom in on what this proof looks like. So in larger letters, we have our variable ts here, and we can think of it as a list, and it contains some types, tau 0, tau 1, tau 2, and so on. And now, we're down here. Here's the soundness proof just repeated. Now this line, again, doesn't type check, because we're asking for the meaning of t0. This p is meant to be prop, but prop is 4 letters long instead of 1 letter long, so it's now p. So here we've got a type error, because we need this thing to be a prop, but if we look up 0 in our environment, we get tau 0, and that's not the same as prop. If we had fixed our environment here to be prop and booleans and natural numbers, then this term would type check. So what we'd like to do is we'd like to find some way to make our environment look like this, but also note that I only really care that prop is at position 0. I don't care that booleans are at position 1 or that natural numbers are at position 2. So I'd like to find a way to say, as long as prop is at position 0, then I'm okay. And the way I do this is I quantify over an arbitrary environment, just like I had before. There I had the type error. But now I say, as long as you have another environment here, this is a constraint that says prop must be at position 0. And now instead of stating that propositionally using an equation, I write this operator, this circle plus operator, that's going to take in two of these environments, this environment and this environment. And we can think of it as, if there's something here, then we copy it down, and if there's nothing here, we just copy what we had above, right? And so now we have an environment that looks like it has p at position 0. And this gives us the extensibility aspect because whatever, for example, Greg wants t1 to be will be copied down here, and our theorem will hold over that. But as long as we have props at position 0. And now this term is well typed because we've taken ts, compose c, as opposed to just ts. All right, everyone can wake up now. This is easier. All right, so now we're going to talk a little bit about sets. So the previous 2 slides or 3 slides that some people slept through are nice for building composable procedures. It allows us to build procedures and put them together. Another thing we want to do is we want to be able to build procedures easily, and so we can toss them into our mix of procedures. So here we're going to take a look at this simple term. X is an element of X's, the set of X and Y union with the set of Z. We might think, we could write some fancy decision procedures in Coq to handle things that look like this, but it might be annoying. Instead, we already have a proof that we could apply at this point. Maybe this proof would take something like this, this goal, and reduce it to this goal by saying, oh, you're in the union of 2 things if you're in the thing on the left. So we could apply this lemma. But we can't do that necessarily in a reflective world because this thing is a semantic object as opposed to being a syntactic object, so we can't inspect it. But our representation of syntax allows us to represent all the interesting features in here, like variable binders and all these symbols like unions and elements of. And so we can build a syntactic representation of this term, and then we can inspect it using generic procedures. So what we do is we solve a problem called the unification problem. We ask the question, what values of A, B, and C will make the conclusion of this lemma match the conclusion of the goal we're trying to do? And so what we can do is we can kind of put question marks in front of this. Says this is going to be a whole, and then ask this question, and it was like, if you pick A to be X, and you pick B to be X and Y, and you pick C to be Z, these things will match, and your goal will be reduced to this. So this unification procedure is something that I coded in Coq, and it allows us to do kind of very generic reasoning like this. So instead of writing your own decision procedure, you can just take a lemma that already exists that you proved. You can kind of take an automatic procedure that constructs syntax from that. So this step from going here to here is kind of an automated thing. Then we can kind of pass this lemma and potentially lots of other lemmas off to this general procedure that I wrote, and it can go through and try to find this proof for us. So this exists in 2 ways, auto and auto rewrite. Auto here is going to do exactly what I showed here. It's going to take a bunch of lemmas and try to apply them blindly until it finds an answer or fails. And auto rewrite is going to take a bunch of these lemmas that express equalities between 2 things. It's going to replace all of them, rewriting from left to right as much as it can until it finds a new value that equals. All right. How are we doing? Good? All right, great. So I talked about open computational reflection. That's my idea of composing composing languages by factoring them through this general language, the lambda calculus. And I talked about how that gets us compositionality, and it gets us customizability because we can write those generic procedures like auto, and we can kind of bolt them on the side after the fact. So now I'm going to evaluate. I'm going to show you kind of that everything I told you wasn't a complete lie. It's not a lie in math, but I'm going to show you how it actually scales, so you can actually be able to prove stuff with it. So we built this system, or I applied my automation to Atom system called Bedrock. It's a Coq library for doing imperative program verification. We have verified, or really he's verified using my stuff, thousands of lines of low-level code ranging from basic data structures to a garbage collector, thread libraries, web servers, things like that. So the same automation underlies all of this stuff. And we note that in each one of these procedures, like this is the collection of basic data structures, things like linked lists, sets implemented as lists, sets implemented as trees, and things like that. Each of these lines has kind of the general stuff that you would expect for reasoning about imperative programs, things like reading and writing memory cells and things like that. But it also has things specific to, for example, linked lists, like I must understand what this linked list predicate is. How can I reason about it, and what does it mean? So all of these pieces are, so the linked list has its own custom automation that's built using that customizable style for verifying this module. The same thing is true for list sets and tree sets and queues. So we can take the generic automation, we can specialize it to each one of these modules, and that specialization is relatively cheap. We find that the overhead of verification in all of these is significantly less than the 20x that other people sometimes will quote as a standard overhead of verification in this very restrictive setting of proof assistance and foundational proofs.
What do you mean overhead?
So here we're looking at, this is the lines of code in the linked list module. There's about 42 lines of semicolons or whatever. And then everything else is considered overhead. So this is stuff that you wouldn't write if you were just writing a C program. This is loop invariants, tactics that don't fit immediately into this procedure. We'll talk about that in just a minute. And then other things, these are things like mostly lemmas and specifications that are going into this a little bit here. So, for example, the definition of what a linked list means in the heap is counted in this column. Any other questions? No? All right. So let's take a step back. Let's look at what does performance look like on the broad scale. So does does open computational reflection make verification faster? And the answer to that is yes. Does it make verification fast? It's reasonably fast. It's not amazing. Here's the overall picture of how verification works in the system in order to understand kind of why the answer to this is reasonably as opposed to yes, it's blindingly fast. So we start with a program here represented by this red box. We do this step called verification condition generation that spits out a whole bunch of verification conditions. We think of these as a path through the program with a precondition and a postcondition. It says if you can prove all of these things, then this thing is correct. It satisfies the property. Then there's some higher order reasoning that goes on because of Bedrock being a very higher order system. We do symbolic execution, symbolic evaluation, which is going to massage this down into this entailment, or this formula implies that formula. Some more higher order reasoning, and then we do entailment checking kind of together with this higher order reasoning in order to get higher order specifications verified. If we break down the time we spent in each one of these, we spend about 5 seconds doing 5% of the total verification time doing verification condition generation. We spend about 4% doing symbolic evaluation. We spend about 16% of our time doing entailment checking. Now, the 16% being about 3 times more than these is reminiscent of the fact that here we're doing it in a loop, so we're probably doing this a lot more times. And it turns out that we're doing it usually between 1 and 8 times per verification condition. So the blue thing here, or the blue bars here, represent things that are coded reflectively, and these 2 blue bars, this 4 and this 16%, are things coded with our style of open computational reflection. The other 2 bars, which really I just have one number that says the 2 bars of these combined correspond to 71% of our time. And so if we take a look at this, when we say, does it make things fast, it turns out that it does make things that we do using reflection fast, but it doesn't make the whole system fast because we're still spending 71% of our time not doing the thing that's making our stuff fast. So this is at a macro level. We might ask, how does this look at a micro level? If we were to apply computational reflection to more of these pieces, would we expect to see a win? How much of a win could we see? Here's a simple linked list function computing the length of a linked list. This is not Bedrock syntax, but it's essentially what the program would look like. Here's the foundational proof that we have to generate in order to figure out that this program satisfies its specification. Here's C1. This proof corresponds to just the loop. So we know x doesn't equal 0, so we're not at the end of the list. We increment the length, and then we go to the next point, the next cell here. So just those 3 lines, essentially, is what's captured by C1, C2, and C3, and the verification of that is this. Without our fancy reflective, without our open computational reflection, we would run our symbolic executor. That would go from this step to this step, and then it would get stuck. It would get stuck because it wouldn't know how to proceed and unfold the list predicate appropriately. So we would do this, we would run it, and it would take a third of a second. All right? Then we would run LTAC, because that's our only choice. We need to do some rewriting, and we don't have the features for open computational reflection. That takes 0.9 seconds. And then we would finish off by running our symbolic executor for the last 2 instructions, or 3 instructions, and this would give us a total of 1.7 seconds. Say, okay, well, 1.7 seconds seems like a pretty long time for this simple verification condition. Can we make it better? And it turns out that if you take the whole thing, using our open computational reflection technique, we can compress the entire thing down to a little over a third of a second. But where does this come from? Because if we just said, well, if LTAC ran instantly, if we didn't have this box at all, then we would still expect to see about 2x. It would still take 2 times more than this. So where are we getting our win from? And our win is really coming from the fact that we don't have to enter this syntactic world and then leave it, and then enter it again and leave it. So the fact that we get to do the whole thing in one reflective call is giving us this 5x performance speed up. And we'd imagine that if we applied these techniques to the whole thing, the end-to-end thing, that we would see similar numbers to this. Are there any questions on this before I proceed? Yeah.
So what's preventing you from doing that? Or what would be involved to actually get all into the reflective world and get this one? And why is that not feasible on the time frame for the Bedrock world?
So Bedrock is using a slightly older version of the system. That's the reason that it's not implemented. So actually, I have current work where we're using a more recent version. The entire thing is reflective, and base comparison with a pure LTAC solution is about 100x speed up. So I don't have the official numbers for that, so I can only give kind of...
Okay, so the reason wasn't you didn't move everything into the reflective framework for the Bedrock stuff is because it's using an old version of it.
Yeah. An old version of this reflective.
An old version.
Yeah.
Okay, thanks.
Yeah.
Is that other work you just mentioned dealing with first-class code pointers and specifications?
It is dealing with function call. Yes. Yeah.
Cool.
It's a different approach to everything, essentially. So. Different approach. I will tell you why it's not that bad in the coming slide. So we talked about composability, scalability, and customizability. Let's take a look. Oh, man. As long as you look at these slides, there's always a typo. So this should be talking about customizability. Let's talk about a whole range of reflective procedures. So we've got really complicated things like permutations, arithmetic. Why I call these things complicated is because they kind of think about things in a very abstract way. So for example, our logic solver might say, if I can sort these two things, these two formulas, and then I can check that they're equal, then I know that one is a permutation of the other, and I can conclude that there exists this entailment. And so that's like not really reasoning about the actual syntax. It's kind of thinking up a level, abstracting the problem, solving a different problem, and showing that any solution to that problem implies a solution to the original problem. But I also showed you these really simple things like lists and sets on that previous slide where you just say, I've got a bunch of lemmas, just like throw them as much as I can and see what sticks. So this is really simple stuff to do. And my question is, what exists in this continuum between them? And the key thing here is these over here were particular set or particular programs like auto and e-auto that I talked about before. And they let us do kind of some level of customization, but it's not as open as we might like. And so what we're going to do is we're going to build a language or a library kind of for writing and composing these reflective procedures. And so this would allow us to take something like a verify, like this procedure would do program verification. It says, if I see a write, then do something like apply this write lemma or apply this read lemma. There might also be other things down here that say, if I see an equation in my context, then substitute that equation around. Or if I see some quantifiers, then start manipulating those quantifiers in interesting ways. So I'd like a way to build these sorts of procedures without having to go in and write a whole bunch of stuff and then verify it kind of in a very laborious way. And the idea is we're going to take intuitions and insights from the LTAC language, which we've seen snippets of before, and we're going to encode them in a reflective style. So here is a sketch of what verification might be, that verify on the previous slide. You say, repeatedly do this thing, do the first of these things that apply, and just kind of go for it. Using this system called RTAC, which I developed, allows us to take this LTAC, which previously, remember, LTAC produces a proof, and that proof is later on checked. RTAC is different because RTAC is an object that's inside the logic. That means we can reason about it, and that allows us to write this theorem and prove it one time, and then use this as the soundness theorem to do the full verification. Right? So while we're going to run this procedure each time we check the proof, we don't have to check any of the complicated bits inside of this each time. And so what we can see is the features up here, like repeat and first, get translated down into object-level functions in our logic. Here, this repeat and first. And our custom procedures, like Tauto, get translated down to the actual fancy procedures that we wrote, like rTauto. So we can take any procedure that we've already written, we can kind of call it from this, and the proofs kind of are going to fit together in a nice way. Mentioned this proof is checked once and for all. And it's nice to note that the soundness of this proof here, is essentially derived compositionally. So there's a theorem that says repeat of t is sound if t is sound, and first of t1, t2 are sound, or is sound, if each of t1, t2, and t3 are, if all of those things are sound. So we can build this in a fairly automated way. The only place where it doesn't work out in a completely automated way is when we have our own custom procedures, and we have to make sure that their soundness proofs kind of fit into this framework. So I'm going to tell you a little bit about what this framework looks like. This will be a little bit higher level, so you don't have to go to sleep, but you might nod off a little bit. We're going to talk about how do we build this generic proof. So here is a goal. You might see, here's our same linked list example. Here I've added this question mark Q for no apparent reason at this point, but it will become obvious later. We apply this theorem, and it says, we're going to do some rewriting. We're going to translate this linked list predicate into a bunch of existential quantifiers and some other mumbo-jumbo, and that's going to allow us to get to this step here. So first thing to note here is we have parallel proof obligations. We have to solve two problems in order to conclude this thing. That seems simple, but it actually turns out to be more annoying than you might think. And it has free unification variables. So in the autoprover, we kind of knew exactly where all of our unification variables came from because we know we got all of them from just applying things. Now, when we solve premises like this, we might add unification variables in kind of arbitrary ways. And we need to make sure and track how they're being introduced so we can know how to eliminate them in the end. The first type of reasoning that we do is local reasoning. It's the idea of saying, if I had some procedure, fancy as it may be, to construct a proof that looked like this, and the conclusion of that procedure just happened to match up exactly with the premise of another procedure, then I could just take this proof and kind of glue it on top of this one. Right? And this gluing is essentially building a bigger proof tree, and it's exactly what the LTAC mechanisms are going to do for us. But we're going to do it reflectively, so we're building this proof once. The cool things that this thing might do is it might introduce new universal quantifiers. So we'll have to solve this goal by going underneath these quantifiers. Now these quantifiers will wreak havoc with our unification variables. We'll have to reconcile those a bit. But it also means we have to be very precise about the phase split between what we know and what we know about what we're reasoning about. That's a little bit weird. We might be trying to solve the problem false implies 1 equals 2. And we know that that's the problem we're trying to solve, and we know some extra stuff about our invariant, the RTAC invariant that this proof search is maintaining as it goes along. If we just wrote this, then maybe the fact that we're in an inconsistent context means that we can violate this and not preserve our proof. So it's very important that this phase split says all the semantic stuff occurs here, and all of the non-semantic stuff occurs here. They need to be split in a nice way. And that's important. It has lots of details, but I'm not going to go into them now. Read my amazing document. Okay, the last piece is called global reasoning. And it's where we take these unification variables that existed here, like Q, and we say, it would be great if Q is equal to P, then we could solve our goal. Well, all we need is this proof that says Q equals P, but it's kind of weird to put it there because we don't have any way to solve it. So what we do is we stuff it all the way down here. We move it all the way from the top down here. And then we have this weird thing. We have to go replay, essentially, all of our proofs and say, if we had this extra assumption, then it'd still be valid to conclude this. If we had this extra assumption here, it'd still be valid to make this conclusion. And this requires a lot of stuff. Remember, we don't actually replay the proof because we built this proof, we proved this theorem sound. The global reasoning property is kind of a separate property you have to prove, and then the RTAC composition proof handles all of this kind of replaying of the proof in a nice way. So we propagate this through the entire proof tree, and we have to make sure that the P up here is valid down here. So now, kind of at the end, so I showed how open computational reflection solves all these nice problems. So, Steve, to your question, this RTAC stuff is the piece that we use to do the program verification in that richer setting. And so we built all of the procedures like verify this program and all that inside of this framework, and that's where we're seeing this. Okay, so we talked about open computational reflection. It's great. We talked about how it's composable and customizable. We showed how it's scalable and how we get trustworthiness from the fact that we're in intentional type theory. Now, for those of you who are familiar with lambda calculi, you might ask, well, we picked the simply typed lambda calculus. That's pretty boring. What about everything else? So there's this cube called the lambda cube. It tells us 3 axes for the expressiveness of the lambda calculus. One axis is this lambda 2 axis, and it expresses polymorphism. Things like this function will work on any type, like the identity function, for example, will take any value of any type and return a value of that type, namely the value that it got in. We can actually handle a restricted version of polymorphism by faking it using special term algebras. And that is, we talked about things like conjunction being a symbol, but we can talk about conjunction applied to a type, giving that a type and saying it exists for any version of the type. It's kind of a terrible explanation. Turns out that it works out very well. We could handle all the problems that come up in program verification using this polymorphism technique. Details are in my thesis. We can also do type functions. These are things like list. List is a type function because we have lists of nats and we have lists of strings and we have lists of strings and things like that. So these are type functions. Turns out we can fake them as well using specialized type algebras. The details are once again in my thesis. If you take kind of the completion of these 2 languages, you get something that's kind of reminiscent of HOL. And that's interesting because while I love dependent types, Hall is a pretty powerful logic, and you have verifications of very interesting things inside of Hall, things like compilers and even microkernel operating systems. So you can do a lot with this language, and so completing this square, the fact that we can fake it means that we can do a lot in kind of a fake sense, but it actually works. And the fact that I've shown how you can do it in general gives you an idea of how you could extend what I've done to do it in a more general context. But one thing that we don't have on this face of the lambda cube is term dependency. And the difficulty with this, that I describe a little bit more in my thesis, is because there's a dependency between types and terms, and it's kind of a cyclic dependency. There's lots of interesting work that goes into this, starting in 2007 and maybe earlier. There's been a lot of people thinking about how do you represent type theory inside of type theory. And so all of those problems kind of wrapped up in this dimension. If we could complete that dimension, then we would end up something out here, and this would be something like coq. And we would be able to kind of internalize coq inside of coq, and we'd say, we don't need LTAC anymore because we have essentially coq inside of coq. Do everything reflective. All right, so that was my thesis. I talked about how open computational reflection inside this context of intentional type theory allows us to build trustworthy, scalable, composable, and customizable decision procedures and automation. These are all the people that are on my committee, I have worked with, am married to, my parents, and then all the people that helped me throughout my 6.5 years of getting to this point. So thank you.